Okay, I know we don't have everybody in here, and I'm hoping that you guys will catch up while you're doing that. Here is the deal. We have lab this afternoon, and I know I promised to do some problems for you from this chapter. We already did one, problem 52, and then we promised to do problem 53, and we promised to do problem, let me look at the book again in here, okay? So problem 53, and we promised to also do problem 55. So that's what we're going to do. And then the other problem that we are going to do, is this it? Yeah, problem 43. We're going to do problem 43, okay? So I don't think that I mentioned before in the past we're going to do that problem 43, but we're going to do it, okay? So it's an important problem. So now I mentioned in probably by mistake, okay, that problem that we did 52 is similar to problem 61. It's really not 61, but 62 when I looked at it. I guess sometimes you have, because now my eyes are not as good as they used to be. But it's clearly problem 62 and problem 47 are identical to that problem that we did 52. Let me first of all look at my notes in here and make sure this is this class in here. And let me go into sharing that screen. What is it? And I thought I shared. Share this screen. Okay, are you guys looking at what it says CH23 right now?
Yes.
Okay.
Yes.
Okay. So this is chapter 22 that we covered. I know that we covered some problem. Did we do? We did 52. Now I'm getting a little bit there. So this is actually the sphere. Yeah, here is problem 52. So we did problem 52 and we made the argument for it and everything else. Let me tell you how to tackle those problems in general, because it's very, very critical that you learn the method. Okay? I told you guys after that problem that you should have the skill necessary to not stare basically at problem 47, but actually start it, okay? And not stare at problem 62, but actually start it, okay? If you are ever in doubt about where you stand in terms of what to do next, all you have to do is come back to your notes on how we tackled problem 52, and you should know what's the next step is, okay? So that is a typical way of solving these problems. Every single situation we dealt with up to that point, before problem 52, dealt with a uniform charge distribution. This type of problems are not of uniform type, okay? Charge is not distributed uniformly throughout the sphere. Charge have non-uniform distribution throughout those spheres. So which means that I have to do some integration. I have to sum things, okay? Because I can't just say rho is constant, it comes out of the integral, and then what I'm left with is the volume of the shape that I have in question. I can't do that. Rho is not constant. That is what non-uniform means. So it needs to stay in the integral, and I have to sum up. Okay, that's problem one. Problem two, it says that yes, it's non-uniform, but it retained its spherical symmetry. So on the one side of the Gaussian surface, I'm on the Gauss's law, I'm going to integrate over the Gaussian surface of EDA. Now, the argument of symmetry in here will make the electric field, first of all, have a radial direction because it's symmetrical. It actually has spherical symmetry. So it needs to point in the radial direction, because if you tell me it's not really in the radial direction, it's pointing somewhere in that point, all I have to do is spin this sphere one way or the other to change that orientation, to change that electric field. And then I ask you, open your eyes now. Look at the sphere. Did it change? You say, no, it retained its spherical symmetry. It's the same thing. then how in the world, why then the electric field is pointing in the wrong direction than what you predicted, what you thought might be? So you tell me, oh, then it's wrong. Then the only way to retain that symmetry is if the electric field is pointing in the radial direction. Then you spin it whichever way, the electric field stays in the radial direction. That's one thing. The second thing also, the electric field is not just radial, but it's constant throughout the sphere. I know if I move away from the sphere, it may not be the same number. If I move inward from the sphere, it may not be the same number. But as long as I am on the same sphere, it must be the same number. Because if you say it's not the same, and this point is different than any other point, this one actually has a 5 Newton per Coulomb, and every other point, pick whatever number you like, 10 Newton per Coulomb. Then I tell you, close your eyes. Spin the sphere a little, and that point that was clearly, you said that it's 5, has moved somewhere else. And now the 10 moved to your location where you were staring at in the beginning. And I ask you, open your eyes. Did the sphere change? Did the charge distribution change? You say, no, it has spherical symmetry. You couldn't notice that it has changed under the rotation that I have done. Then I ask you, why then the electric field has changed now and got a new value on that sphere, on that point in the sphere? You say, oh, then it must be the same because it has spherical symmetry. Then the arguments of the spherical symmetry still hold true in this case, even in the uniform and non-uniform distribution of a charge, because of the spherical symmetry. So in this case, when you rotate one way or the other, the electric field must be radial and also the same on the same sphere. That's why it comes out of the integral. And this contribution in here, what is it? When we did, where did we apply it? Actually, just remembering it. On this side, because of the spherical symmetry, E comes out of the integral, and all I'm left with is the area of a sphere, which is 4 pi r squared, okay? However, on the other side, I have to really integrate through R, and I have to know how R changes. If you are ever encountered with this problem, the element of volume that you will need for solving this symmetrical problems for a sphere is this one, 4 pi r squared dr, okay? Can convince yourself one way or the other that that's a sphere. Basically, all you have to do is just take the volume, all you have to do is take a sphere of 4 pi r squared and increase its height a little by dr. And now you have this in area 4 pi r squared moved up a little by dr. Now that's the volume, 4 pi r squared dr, okay? So again, if you're stuck trying to find the charge, this is where you probably went wrong on the calculation here. You did not plug in dV correctly. This is rho, by the way. This is still the charge density, okay? So that basically, in a nutshell, what the method is all about. You have to find the charge, whether all of the charge or just the charge enclosed if you are inside the sphere, okay? Depends where you are, doesn't matter where you are. That is the technique for doing this calculation. As a useful transformation, and we usually almost always we do this transformation. R over big R is just a dimensionless number. We usually introduce this variable u in the calculations. And basically, instead of doing the calculation over the integral over little r, we do the integration over the dimensionless number u, which has no units, okay? So the integral at the end will just become a number. In this situation, because of this problem, the way that it was chosen, that number was 0, which is good. I mean, we always can like 0. But it's not always true. So this integration, everything else is taken out of the integral, all the dimensions, and you're left with something that you basically should be able to handle, namely the dimensionless unit, okay? So this is basically how this process works. And this is true for problem 47 and for problem 62, as much as we did it for problem 52, okay? Just in the middle of these two problems, okay? Now, problem 62 has a little bit more detail in it than these two problems, because right from 0 to half radius r over 2, you have one type of charge distribution, which is linear in R. And then as between r over 2 to r, you have actually a quadratic dependence of the charge on the r. on the distance from that point on. And then after r greater than r, of course, there is no charge outside the sphere. So this is a piecewise definition of this charge distribution. It's still non-uniform, and you still be able to carry the calculation. Now, because the function is defined piecewise, and if I really want to find the total charge in this case, I have to integrate from 0 to r over 2, the first definition of rho, and then from r over 2 to r, the second definition of rho, and sum up the two quantities, and that's going to give me the charge overall, okay? Or whatever I'm after, okay? So now the electric field may be different between 0 to r over 2 than between r over 2 and r, okay? So that's where r, I'm referring in here to big R, not little r. R is a variable. Little r is a variable. It changes from 0 all the way to infinity. And as it crosses to half a radius of the sphere, to the radius of the sphere, to outside of the radius of the sphere. Do these problems make sense to you guys so that you can start them or not? In light of what this problem 52 is? Yes or no? I need someone. It could be yes, it could be no, it could maybe. Somewhat, basically.
Wait, can I see the part where you plugged in like the derivative of the volume?
Okay, let me go back into sharing the screen. This one?
I think it's the Q equals derivative of, is that derivative of P up there, dV?
Okay, this one, rho dV?
Yeah.
Okay, by definition, let me first of all share with you the details. By definition, the charge distribution rho is equal to dq over dv. Okay, how much of charge is inside an element of volume? So this is the amount of a charge inside an element of volume. Sigma is by definition dq over dA. This is the amount of charge per unit area. Lambda is dq over dl or dq over dx. This is the amount of charge per element. This is dx, by the way, per element of length. Okay, this is a bulk distribution of charge. This is a surface distribution of charge. And this is a linear distribution of charge. On a rod, for example, it's so thin that we neglect its cross-section. Then in this case, all we care about is how much charge is per unit length. On a plate, for example, it's so thin that doesn't have any bulk size whatsoever. It's all of it is basically a surface. Then all we care about is how much charge is distributed on the surface itself. On a bulky sphere, for example, in this case, we want to know how much charge is inside each element of volume. Okay, so those are the definitions for this, guys. Now, when we integrate in order to find the total charge, let me write this stuff below in here. I know we have space at the bottom here. So when I'm trying to find the charge Q, then it's rho dV integrated through the space or through the volume. Obviously, because of a spherical symmetry, I can take advantage of dV and write it conveniently. If I want to find the charge distributed on a thin, basically a plate, then it's on a surface, then the integration, and that is sigma dA. and again, probably have some symmetry there too, that I need to take that dA, and instead of doing double integral, I just end up with a single integral. On a rod, for example, it's the same thing, the integral on the entire line in here of lambda dx, okay? So that is basically typically how we do this. If rho were constant, it comes out of the integration. If sigma were constant, it comes out of the integration. If lambda is constant, it comes out of the integration. That means they are uniform. If they are not uniform, then you can do that operation. You have to leave them inside and do the calculations. So that's the point of this exercise in here. The point of problem 52, rho is not actually constant, it depends on R. So we needed to find, because of the spherical symmetry, we needed to find a definition for dV. And dV in spherical symmetry is 4 pi r squared dr. And now I know what the function rho is, a function of R. And basically, it becomes the integration from 0 to wherever you want to of this R, for example. If R happened to be big R, that means you're looking at the whole charge everywhere. But if you are looking just on a small volume inside the sphere, then you're just looking at the enclosed in that space in there. So the Q enclosed in this case will be this function of R, which I'm going to change the variable quickly in here to make sure that this is actually a dummy variable. Okay. So once I integrate over R prime, then I plug in the value of R prime being equal to R in the upper limit and R prime equal to 0 in the lower limit. Okay. So usually we don't do that. Even in calculus, I remember we don't do that. So we leave this as rho of R, 4 pi r squared dr, because we're sick and tired of getting this R prime. The only thing is we have to remember at the end that R is equal to R in the upper limit and R is equal to 0 in the lower limit. And this can be confusing a little bit into how come this, but that's just because of the boundaries integration of this entire derivative, basically. X stuff makes sense to you? Yes? Jake, was that your question or is it something else?
Yeah, that was my question. It makes sense.
Okay. How about everybody else? Do you guys feel confident that they can tackle problems 47 and problem 62 on your own? Basically, Gonzalo?
Oh, yeah, that makes sense. It's all good.
Okay, very good. As long as you guys go step by step, methodically, and if you find yourself not sure about the next step, just look at the example that we did and basically move on. Now, if you get stuck really and you're not sure about the next step, please let me know, okay? Because I'm not asking you to turn in this stuff in here, at least on Canvas, but I'm trusting that you guys will spend honest time trying to go through these things, okay? Yes?
Okay.
Okay, thank you. Okay, so I'm gonna do problem 53 because as I was telling you, when I first learned it, I thought that was the most clever thing there is. And then we're going to actually continue with chapter 23, okay? And then after that, we're gonna do in the afternoon, problem 43 and problem 60, no, not 60, problem 55, because problem 55, you know guys, how I feel about this kind of problems. They're number problems and they help you really learn physics. So they're very, very important that we do this kind of problems because that's what we do in the lab if we're ever going to do lab. And that's actually what you do as a physicist too. You have data, you have to interpret it and connect it and see if it makes sense to you, what you can, the information you can pull from it. Problem 43 is of also extreme importance. So it was not on the original plan, but I just added it. Okay, so let's look at problem 53. It's probably a good idea to open a new tab in here because it's too crowded in there. Problems from CH23. Okay. So problem 53 is the following, basically an insulating, and it's a key word when you guys look at these things, okay? So they say the first word in here, forget about the article in there, is insulating. And we talked about what an insulator is and what a conductor is. So when they say it's an insulating, that means the charges are anchored to their atoms and they cannot move freely. That means if I take charge distribution and put it in that insulator, it's going to stay where it is. It's not going to move around. In a conductor, on the other hand, it cannot stay in the bulk of the material. It's going to move to the left or to the right, depending basically on until it balances, until there is no charge, until it tries to get it from outside and it cannot. So the charge will end up being basically on the surface, but not inside the bulk of the material. So that is a conductor. Instead, we have an insulating material. So these are some of the key words when you're solving problems to look for. So if you're really looking at a problem, look at these key words and what they mean. Okay, they have a meaning in this case. So you really have to, while you're trying to solve a problem, the first thing is understanding the problem, because if you don't understand what the problem is asking, you have no idea basically how to tackle it. So it's probably sometimes when you're confused about a problem and you don't know how to enter it and you don't know how to do it, chances are you don't even know what the problem is asking. So you really have to understand what the problem is asking and also what is given in the problem. There are so many hidden treasures inside those statements in there, okay? And if you are able to pull them out, now you're in good shape. So problem 53, an insulating sphere of radius A, so it's a sphere, so it has spherical symmetry. If this thing is retains it, has uniform charge distribution rho. So we have a sphere here, and it has a radius A. Okay, and it has a charge distribution rho that is uniform. This is what that means. Rho is constant inside the sphere. Rho is constant not everywhere, but inside the sphere. So that is what that word mean when they say it's uniform. Okay. The sphere is not centered at the origin, but at r equals to b. So the sphere is somewhere in space, actually. So this is the x-axis. This is the y-axis, and this is actually the z-axis. This is the origin of the axis. The sphere has this location in space. This is where it's located. B, this vector is B in space, okay? So if you're curious about its projections, it has the y, or b sub y, this is b sub x, and this is b sub z. So it's a vector in space that is bx, by, and bz. Any numbers will do, okay? As long as it's not 0, okay? And show that the electric field is E, that is what they want you to show, okay? That it is given by, this identity, we need to prove it, by rho divided by epsilon naught, or 3 epsilon naught, I should say, times the difference between R and B. Okay, inside the sphere. So that means take this point inside the sphere, this point. This point has coordinates in space R. So this point specifically P has this coordinate R. And this is the vector R minus B. Okay, so it's this vector, and this vector actually points in this direction. Let me go back into the lecture notes and see, because we did this using Gauss's law. For a sphere, where we took the origin actually is the center of the sphere. That's why we did this calculation. And it was in lecture when it was uniform, not the problem that we did, not problem 52. It's problem when it was uniform. So when it was uniform, if you guys remember, here is the value for the electric field. So we took a charge distribution that is uniformly distributed, and we did the calculation for the electric field with Gauss's law. E times the area of the sphere is equal to rho times the volume of the sphere, because rho comes out of the integral, and all I'm left with is the volume of the sphere. And the value turned out to be rho. In this case, we wrote it as E equals to rho divided by 3 epsilon naught times the vector R. And the vector R is points from the point in space so from the origin to where the point P is. So this is the vector R. The electric field is in here, and this is actually where the vector R is. Okay? It points from the origin of the sphere all the way to the point where we want to find the electric field. So I'm going to use that expression for this problem in here. So in that point P, it's clearly the electric field E. So I'm going to call this vector, for example, R prime. So this is R prime actually. And it's clearly from the point A, from the from the center of sphere to where I want to find the electric field. So this electric field must be equal to, according to the lecture, rho over 3 epsilon naught times R prime as a vector, where R prime is the vector from the original sphere to the points in there. If you don't trust this, all you have to do is invent a sphere in here of radius little r prime, and you make the case for it that the electric field is radial, and furthermore, it's uniform throughout that sphere because of the spherical symmetry. If you spin it one way, it doesn't change. So times the area of 4 pi r prime squared is equal, that is the area of this sphere, must be equal to the charge enclosed divided by epsilon naught. The charge enclosed is rho, which is constant, times the volume of the sphere of radius r prime, and the volume of the sphere of radius r prime is 4 over 3 pi r prime cubed. So cancel the cube with the r prime, cancel the 4 pi with the 4 pi, and you will be left with rho over 3 epsilon naught r prime. But you argued that the electric field is radial, and this is the radial direction. It's actually r prime. Therefore, E as a vector must be equal to rho over 3 epsilon naught times the vector r prime pointing in that direction. Okay? It's clear from the geometry that r prime is the difference between the two vectors. Let me redraw the geometry clearly in here. So we have the center of the sphere in here. This vector is B. So I'm going to exaggerate that location again in here and say this is the point P that has a coordinate R. So this is the vector B, okay? And this is what we were talking about all along, being R prime as a vector. You can clearly see from this geometry in here that B prime as a vector, B as a vector, plus R prime as a vector must be equal to this vector in here. That is their sum. So from here, we're going to conclude that this R prime is nothing but R minus B. Okay, so you guys see this geometry or not?
Yes, Professor.
Okay, very good. So all we have to do is plug into that expression for the electric field, and we are in business. We answered it basically. I know I went a little bit in detail about it, and probably doesn't deserve that much detail, but it makes a point in here that this is actually R minus B, but it has to be careful in here. This is inside the sphere, not outside, because outside drops like 1 over distance squared. So you have to be careful in here. So inside it goes like this, okay? So this is part A of the problem. Part B, an insulating sphere. Now this is a different problem. Part A and part B are different. So part A talks about a sphere that is not centered in its origin, in its center of symmetry, but centered somewhere else. I mean, you're calculating the electric field with respect to another reference frame. So you're doing translation, and that's exactly what that is. We did a translation of the coordinate system by an amount of B. We shifted the origin from 0 by distance B, and therefore this is the expression for it. So this is part A of the problem. So this is problem 53, if you guys are not, from this book. I think from the other book was problem 57 or something, okay? I have the 14th edition in here. Yeah, it's problem 57 from the other edition, okay? 14th edition, that is. So again, we want to find part B. Now, what you have an insulating sphere of radius R, has a spherical hole of radius A. So what we have in this part now, we have a big sphere. And this sphere happened to have a radius of R. And inside of it, at a distance B again from it, we have another sphere of radius A in such a way that A is less than B, because if A is actually equal to B, then we have a problem, because it's going to expand all the way to this point. Furthermore, B is less than R, which puts it right in this direction, okay? So this is our little hole. So there is nothing in there. So this is a hole, nothing in it. So the charge is here. Okay, so there is a rho charge in here per unit volume, okay? They tell you that, okay, condition in here. So this radius is A, by the way, where A is less than B, which is less than big R. So that this geometry is clear now, okay? And so they show this crossing. So this is a sphere, not a circle, okay? So you have to be careful in here. This is a 3D picture. All we're doing is taking cross cut from it, okay, on the plane. The solid part of the sphere has a uniform charge distribution rho. So rho is constant, okay? Rho is constant. That's important, usually for our sake here. Constant inside. I cannot call it a sphere anymore because it's not a sphere anymore. Inside the shape. And I have to be careful here. It's actually a 3D shape. Okay. Here is the question. Find the magnitude and direction of the electric field E inside the hole and show that E is uniform over the entire hole. So find E somewhere inside, here, for example. Okay, and show that the electric field in that point is uniform. Here is the trouble with this reasoning. Here is the trouble with the problem. I cannot really use Gauss's law for the big sphere, because if I were tempted to use Gauss's law, I don't have symmetry. I don't have spherical symmetry, because if you close your eyes and I turn or spin the sphere one way or the other, you're going to tell. The hole has moved from one location to the other. So that point P is clearly not in the same place. Till you look at that point in space, when I spin it, it may not even be inside the hole, the hole at all. It might be somewhere else, okay? So there is no spherical symmetry. So you cannot do that part. You cannot take E out of the integral and multiply it by 4 pi r squared, because it's not going to work. You really have to integrate. You have to sum E throughout all of this space in here to do it that way. Not only that, but the charge enclosed also has a problem on the other side too. And it's not 4 pi r squared dr anymore for the dv. It's not correct anymore. I have to use the full-fledged expression if I want to really write the polar coordinates, namely r squared sine theta, d theta, d phi, and then dr, okay? Where theta varies from some weird changes in here and have to go around this value when you are there and then come to the same thing with phi, actually. Okay, it has to change in such a weird way also. And so basically rho is not constant throughout. So not only it's not constant, there is no symmetry. There is no symmetry. So Gauss's law is a no starter. You can't go there. You can't try to even work your way back to chapter 21 and do the actual integration and find the electric field. Let's say, for example, you take a point volume in here where the charge rho dq, rho dv, I'm sorry, where rho is constant, is going to come out. Don't worry about that part. It's going to be of this type, rho dv over 4 pi epsilon naught times this distance squared. Okay. I'm going to call it r prime now. And then times the r hat prime, which is this vector in here, and the integration is a mess. You're not going to be able to do it. It's very hard. It's not very hard. You have to really get a computer to do it. And it's going to be very complicated and depends on the details of the shape. And it's not even, you're not going to get something easy to work your way through. If you do it with computer, you'll notice though, that depending on the precision of the computer, that you're going to get a number. And that number seems to basically be fixed, whether you calculate the electric field in this point, or that point, or that point, or that point, or that point. And it's close from the correct answer. But the point being in here is that this is a very, very hard problem to do, either with chapter 21 or with chapter 22, namely Gauss's law. So instead of actually doing this extremely hard problem, this is what we're going to do. We're going to do a hypothetical problem, not this problem at all. We're going to do another problem. So a mathematical problem. So this is what the problem is. What I'm going to say in here, I'm going to take my entire sphere and smear it with rho. So there is no hole anymore. Okay. Obviously, I filled the place where the hole was with rho. Okay. And I can calculate now the electric field in that point using Gauss's law. And we know what that value is. We know actually for this one, for a sphere, for this sphere, the electric field due to the entire hole in here. So I'm going to call it E1 in vector also, where this distances are to the point, is going to be simply rho over 3 epsilon naught times r vector. So we know that. That's what we did earlier, okay? And the origin is actually in this point in here, so that there is no displacement or anything like that. But then I have a problem. This is not the problem that we have to begin with. We have a problem where there was no charge inside that one. So what I'm going to do now, I'm going to take another sphere of radius A and come to that same point. This is the same point, by the way. But the charge distribution in here, I have to make sure that it's actually negative rho, not rho, but minus rho. So I have a minus rho in here. I don't have a positive rho. So that if I take this shape, this point, first of all, will sit on top of this point. And this distance, obviously, it has to be an r prime now. It's not the same r, okay? But the charge will cancel because I have a rho per unit volume and I have a negative rho per unit volume. So I add up to 0. You guys understand? So now I can find the electric field for this one. And that's I'm going to call E2 now, with a charge of negative rho. So it's going to be minus rho now over 3 epsilon naught times r prime. So those are the two spheres that I have. Obviously, I separated them just for my convenience. The actual thing is these two spheres are on top of one another. So this sphere is actually here in that where the hole is supposed to be. Okay, and it has the right radius and it has the right charge distribution to make sure I don't have any charges. Okay, so now using our BFF, do you know who is? Do you know what we're going to call now? Do you know who he is? Our best friend forever in this class.
Superposition principle.
Thank you very much. Have a nice day. Okay. So it's the superposition principle. Because the way this works is, you assume the other sphere doesn't exist with the negative rho distribution and calculate E1. You assume the big rho distribution with the big radius r doesn't exist and you calculate E2 due to the sphere. And now, by superposition, E is simply E1 plus E2. Okay, that's it. So isn't this smart? I thought this was the smartest thing ever, honestly, because that problem is inapproachable if it were not for this method in here. Okay? So now E is simply equal to, they have the same rho over 3 epsilon naught, except one of them is positive and the other one is negative, of r minus r prime. And if I go back into my geometry in here, let me show you basically what's going on. Okay. This vector is a vector B again to the center. I need to have different color because we have too many blues in here. So this distance is B vector, and this distance is r prime, and this distance is r. So basically, let me draw the geometry big time so that we see what's going on. So we have r to the point from the origin of the sphere, and we have B to the center of the little sphere, and this is r prime in the expression. It's clear from this geometry, you guys see that r is equal to r prime plus B. And if I want to find r prime minus r, or r minus r prime, I'm sorry, because that's exactly what we need in this expression. We need this difference between these two vectors. That is clearly B. That is the difference between the two centers of the spheres. Now, the electric field then is simply equal to rho B as a vector divided by 3 epsilon naught. Anywhere inside this hole. Okay? And it's constant because it doesn't change, because B is fixed in magnitude. Rho is fixed in magnitude. Epsilon naught is fixed in magnitude. 3 is fixed in magnitude. So the value doesn't change and the direction doesn't change. So it's uniform and equal to that value. Isn't this amazing?
It does make it a lot easier.
Yes.
Because we're
Yeah,
essentially just subtracting the inner from the outer, and that's it.
Yes. It's amazing. Honestly, if you think about the problem and if you didn't know about this method, it's really a nightmare. Okay, you're working on a project, for example, and a mouse chew from your fiber optic device, for example, and you would want to know what's going on in that field. Use the field for that point in there. Use this method in there. Okay, somebody had bite from your charge distribution or something. So use this method. It's very clever. As a matter of fact, problem 54 is identical, except the symmetry there is not the same. I mean, it uses a cylindrical symmetry, but the same difficulty in the same thing. If you have, for example, a wire, for example, for electrical, for Ethernet, for example, okay? It's a tube of so many wires, and the current sometimes is flowing this way, the current is flowing the other way, and you're interested in the magnetic field produced by this ones. You can use this method too. Or for example, if you have a conduit and you make another hole in it where you have another wire, for example, for insulations or to drive the wire or something, but you're interested what's going on in there. There is interference in there or not? So all kinds of applications that you might think of in here, okay? But this method is a very clever method. I thought that this is a smart thing to do. I mean, to make a problem that is hard and work your way through it and argue your way through it through this not real problem. This is a mathematical situation. I don't really have a charge distribution of negative rho. That doesn't exist. I only have this situation, charge rho uniformly distributed through this shape. And this shape is not a sphere anymore, okay? Where there is a hole, a spherical hole inside the sphere, okay? And that's it. That's the real problem. That is actually the actual problem. So what we do in this case, we invent a problem, in which case the entire sphere is smeared with that rho. And now to make up for that additional charge that we placed in there, we just take the right amount of distribution, which must be exactly equal in magnitude. That must be rho in magnitude, but the opposite in sign to cancel the other one, so that there will be no charge in that place, as if this is the problem that we have in mind. And then we do the math, and it's very straightforward, very easy geometry to deal with. And you have the answer, okay? This method, by the way, and I already alluded to a magnetic field, is there too for the magnetic field. You probably have done similar problems in physics for A involving either the center of mass or the moment of inertia with this same technique. And in there, instead of course, the charge, the mass density or the density, what we call density in general, is positive number because the mass is positive. But then if you have a hole in your matter, you assume that you have some sort of a negative mass to compensate for that positive mass, and then you solve the problem. And it's a very useful technique there too. If somebody is not aware of what you're doing and you didn't tell them that this is a mathematical, basically hypothetical mathematical model to solve the problem, they would raise all kinds of crazy thing about you. You have a negative mass. What did you come up with negative mass? What is negative mass? But then it's not real. It's just a mathematical trick to solve the actual problem because I don't have anything in there. Since I put, for example, 5 kilograms in there, I need to remove those 5 kilograms and put a negative 5 kilograms in there to compensate for that additional mass. So you're drawing actually on the screen a sphere with a negative 5 kilogram. And if somebody doesn't know what you're saying, what you're doing, they will be basically, you have negative masses. What is that supposed to mean? So if I have a negative mass, it's not going to fall to the ground. It's going to fall to the ceiling. Okay. Which is kind of I mean, if we have negative masses, they will be stuck on the ceiling all over. Okay. Because remember, mass times gravity, and the force of gravity then will pull them upward. Okay. So this is a very powerful technique. So that's why, see, now you have at least 2 ways of tackling these problems. You have so many problems and you're going to deal with them, you're going to solve them. The first one has integrations and stuff like that because of non-uniform stuff, and you have steps during which you solve the problems. So hopefully you master those skills because it's a skill, it's nothing else, okay? That's what I really want you to get from this class on how to tackle these things. And then the second one now is kind of mathematical tricks to do very complicated problems and come up with clever ways of handling them, okay? So this is another one. As a matter of fact, like I said, I mean, I learned it, of course. I wish I'm the one who discovered it, but as I learned it, I mean, I was astonished, okay? And from there on, every time there's a problem, try to see maybe there is a way to do things, okay, from what you've learned, the tricks that you've learned in class. So that's one. The other thing that, the other problem that we're going to be doing is problem 43, and then the data problems, which are the main job of physicists in laboratories and everywhere else, okay? And even technicians and engineers, they deal with that type of problems. So we need to do that too, because that's basically what you will be paid for, to do your job as an engineer, okay? So I'm going to defer those 2 problems to later on when we meet in the afternoon. I know it's 11:20 already. We still have a little bit of time to finish these things, and we are going to meet at, what time do we meet today? 5 o'clock?
Yeah, 5 o'clock.
Yeah, 5 o'clock, we're gonna meet, and you guys hopefully will go through more problems and discussions and things like that, and learn actually some fantastic stuff with problem 43 that I believe are very powerful stuff. So you need to do those things, and also problem 55 also, okay? So do you have any questions before I go into chapter 23? Let me add a page in here. I know we probably, we introduced 23, didn't we? Oops. Problem, let me go to the lecture notes in here for chapter 22, just to make sure. Get it to the conductors. We did and I told you about how important this relation is. We did this problem. No, we didn't introduce chapter 23. Okay. So let's get to the stuff of chapter 23. Okay, here is the stuff that you guys probably remember from your physics. Aren't you guys sick of chapter 22 already? Because I am. We did a lot in it. Gauss's law. So we need to have another method now. And this deals with the electrical potential. When you guys had physics 4A, of course you learned F equals to ma, no?
Yes.
Okay, so that is basically, I'm gonna write it this way, but it's fine. Whichever way you write it is fine. You were in chapter 6, I believe, in the book when you discovered that this law leads to this theorem, this great theorem, which states the following, that the work of the force is equal to the change in the kinetic energy of a system. This was called the work energy theorem. You remember this theorem?
Yes.
Yep.
Yeah, where
Yep.
where the work basically was defined as the force times displacement. I'm writing it in general, okay? I know you did mainly 1D. In doing 1D, you found this basically that the work, basically here is the premise. Here is what this is saying. An object goes from position 1, or state 1 to be more specific, state 1, to state 2, okay? And it goes through a path, it doesn't matter what that path is, and it ends up being in here, okay? During its entire journey, it goes through changes in its motion, changes in velocity in such a way, if it's in here, it's subject to this force in such a way that this force is equal to m change in velocity over the change in time. I'm assuming that there is some ticker in here that keeping track of the time. So this happened at t, this happened at a later time delta t. The velocity of the object was here, and now the velocity of the object is in here, so the velocity has changed by this amount, okay? And the process. And the ratio of delta v over delta t is exactly the acceleration with which this object is undergoing, okay? So the force is changing acceleration constantly. I mean, changing velocity constantly at the rate of the acceleration, okay? In taking the object from position 1 to position 2. I know that, we know F equals to ma. Granted F equals to ma, okay? The question then was, how does the force do it? Well, the force, apparently what it does is, according to this theorem, it's going to do work. The force works to do what? To change the kinetic energy. That is basically what that of the system. So this was located at position R1, and now it's at a position R2. This turned out to have a velocity V1, and now it ends up with another velocity V2. This state actually I can define a kinetic energy in here, which is 1/2 of mv1 squared. This I'm going to define the same quantity in here. Take the difference between this final and this initial, and that's going to be the work that the mass does in going from state 1 to state 2. State 1 is defined by everything of index 1. State 2 that is defined by everything index 2. Okay. The transition between these two states is the work the force does. So that is the secret of how forces do change kinetic energy. That is, in a sense, we were led to this result from F equals to ma. In other words, F equals to ma leads to this result. There is another part of actually the theorem, I don't know if you did it in physics 4A or not, that if I start from the work energy theorem, I can end up actually with F equal to ma. Modern physics doesn't start from F equals to ma, it starts from something equivalent to the work energy theorem. Okay, quantum mechanics, relativity, and even classical mechanics, the one that you did in physics 4A. In some textbooks, for example, Landau starts with this statement, starts from the energy and works it down back to F equals to ma. So F equals to ma is not fundamental in that sense. If you start from the work energy theorem, it becomes just a consequence of the work energy theorem instead of the other way around in this textbook, where you start from F equals to ma and you will build yourself toward the work energy theorem. It is a powerful, powerful theorem that goes beyond physics 4A, because in physics, for example, 4D, there is no position. You can't do F equals to ma. For example, in quantum mechanics, you can do F equals to ma because there is no position. An electron doesn't have a position. So you can't define its velocity as being the ratio of the position over time, because that's not the way to do it. Okay, you can have velocity, you can have momentum, but it's just coming from the consequences of the energy, the so-called Hamiltonian there. Okay, so that is the approach that you really have in that sense. So that work energy theorem gave you a flavor, a taste in your tongues of what to expect in modern physics, okay? That's why it's important, okay? Forces turn out to be two kinds of forces, though, when you dealt with that problem. There are two kinds of forces. There is the force, this one, that does not, for example, depend on the path. You can go from here, circumvent the entire universe and come back to this point in here, and the work is going to be the same, regardless of the path. Those so-called forces are, that don't depend on the path, are conservative forces. Conservative forces. Okay? There are forces that depend on the path, like friction. Okay? That depends on which path you take. Those forces are non-conservative forces. So conservative forces do not depend on the path, whereas forces, non-conservative forces, I'm going to write them as NCs, their work depend, the work in this case depends on the path. Let me give you an example, okay, from what you guys did in Physics 4A. You have a spring, for example, in here, attached to a mass, and I stretched it. This is its initial position, okay? This is x equal to 0, and I stretch it to an amount x naught, okay? The force on the spring apparently is equal to minus kx, and the energy, the work that does in this case is force times displacement, and is going to be equal to minus this number in there. But we're going to get to the concept of potential energy very quickly. So if this were to start from this location and end up in this location, then in this case, the force of the spring doesn't depend on whether or not you went straight out, or you compress the spring until it's completely decompressed, and then you came back. So that is the same work in this case. Or you could have gone one cycle completely back and forth. It's the same work. You could have gone through this stage, which is straight out, or you can have gone only once, back and forth, basically. Or you have done a whole cycle and a half, basically, in this case, stage 3. So this is my starting point. This is where we are at x naught. The end state is always x equal to 0, x equal to 0, and x equal to 0. So my starting point and ending point is the same in this case. Friction, though, is not the same. Friction depends. If you just come out this way, then in this case, you spent work in the force of friction through this displacement. If you go all the way to the other end and come back, the friction will do work all the way to this way and will still consume energy even in the other opposite direction. That's why there is more friction work in the second process than in the first process. And there is even more work of friction in this case from the third process going all the way to the end. You are still dispensing of energy in the form of heat in this case, all the way to this cycle and coming back. As a matter of fact, this picture is not perfect if you do it with the friction, because you cannot come back to the same starting point, because you will lose enough energy so that your starting point now is not reachable. So you're going to end up somewhere in here where the object stops and come back until it completely stops, okay? Because of friction. So what you do in that situation, so friction is non-conservative force. So if you really want to go back to the same starting point, you have to put an engine, you have to put a motor and supply energy to it. So by the time you're losing heat, in this case, energy in the form of heat. So in order to reach the same point, you have to supply energy to reach that same point in there, x naught. In doing so, actually, what you're doing, you have another non-conservative force, and that force is coming from the motor, from the engine. So that supplies energy to the system, and that, in a sense, will bring the system back in here. Both of these two, friction and engine, by the way, are non-conservative forces, whereas the force of the spring in here is conservative. Because if you guys remember, the potential energy, and in other words, I'm going to look for the work in this case, minus kx times the force of the spring, and a displacement, they are usually in opposite direction. So in this case, the dot product will give me dx, and this is basically the work in displacing due to just the spring in this situation. by this amount. So if I integrate this expression, the work is going to be turn out to be exactly equal to, did I put the wrong sign? I think I did. I'm sorry. The sign is negative. So it's supposed to be negative. So, or, oh man, I have to go all the way just to make the fix the, okay, dx. So this is actually the amount of work in this situation. So the work in this case will be negative 1/2 of kx squared, okay? Evaluated between x naught and 0, okay? So in this case, the force of friction will give me 0 minus minus, so it's going to be actually positive 1/2 of kx squared naught, okay? So that's how much the force of friction will do work actually, because during this stage, it's the force of the spring that is pulling down this object. That's why this work is positive, okay? That's why this work is actually positive in this case. Whereas in going from this point to this point, actually the force of the spring now is pushing back, and the energy and the displacement is in this direction will turn out to be exactly negative all the way here. But in going from this one is going to be positive and compensate for that negative work. And at the end, we'll be just left with this amount of work regardless of how many stages. So during the stage of decompression, of compressing the spring, I'm sorry, during that stage, the force of the spring is pointing one way, whereas the spring is compressing in the other direction. So the work will turn out to be actually negative because you're increasing from 0 to some finite value. So the integral is going to involve also 1/2 of kx squared. So, but the final value in this case will be a bigger negative than the 0. So we're going to have a negative. But in the opposite direction, it's going to be similar to this value, and it's going to compensate for it. So by the time you reach this point in here, this contribution of back and forth will be 0, and you will stay with this amount that you started with. If you go through the steps, it's the same thing. You will have positive contribution, negative one, cancellation of this one, another one in here, negative, a cancellation of that one, and at the end you will be left with just this, the first amount. So it doesn't depend on the path. The friction does depend on the path. You guys remember, it's mu k times the normal force, in this case, times the displacement. The displacement is actually going from this distance plus this distance plus this distance, and the force is always opposite to the direction of motion. So if you're moving this way, the work in this case, the force is pointing this way and the work is negative. That means you're losing energy in the form of heat. You're losing energy also still in the form of heat. So unlike the spring force, which changes direction, the friction will keep basically its direction in this case, because the motion is happening this way. When you turn around, the friction will point in the opposite direction and displacement now. So the work is always negative and you're losing energy throughout any cycle. So the work of force of friction is non-conservative. It changes depending on the path, depending on which way you go from your starting point to the end point. Whereas in this case, the force of the spring doesn't do that. As a matter of fact, we define the potential energy. And if you guys remember that, for the spring, U is simply equal to 1/2 of kx squared, okay? So that is basically the potential energy. And you come up with a work energy theorem in this case, and not a work energy theorem, you come up with a conservation of energy, and you say that the total mechanical energy is sum of the potential energy plus the kinetic energy, okay? And you interpret this as conserved only, so it's constants only, if there are no conservative forces. If there are conservative forces, the change in E is 0 only when there is no conservative forces. In general, it's the work of the non-conservative forces. If there is friction, the system will lose mechanical energy due to the friction. If there is a pump of energy due to an engine, well, there is a plus in the energy. So the mechanical energy will increase in this case because you have the system pumping energy into the system. So we saw that, okay? As a matter of fact, we defined, if you guys remember, the force in that situation to be just minus du over dx. By definition of du. By definition of the potential energy. And we needed this minus sign because of the fact that for only beautification, to make this expression look symmetrical, that's all. For this plus sign. For this to have a plus in there, that's all. If we didn't put a minus in this definition, we will have actually the kinetic energy minus the entire derivative of the force. And people didn't like that minus sign. So they called the antiderivative of the force with a minus sign as the potential energy. And it has this interpretation now. So we know what it means, okay? So if you're curious, for example, for the spring, it's when minus kx is equal to minus du over dx. So if I integrate this expression in here, it's going to be the minus cancel the minus. So what is the function that gives me kx if I take its derivative? It's 1/2 of kx squared. Do you guys remember that? Plus a constant, of course, because of this fact that I'm integrating. Do you remember the potential energy for spring being 1/2 of k times the spring constant, the spring elongation square or contraction square from your physics 4A?
Yeah.
Yeah, good, good. So this is the stuff that, as a matter of fact, we can do even the gravitational potential energy. Gravitational potential energy, again, you are at the ground in here, you take an object and you move it up. So the object has a minus mg weight in this case, because it has a minus mg. I took the sign out, okay? Because I already pointed with the vector. As a matter of displacement here, upward. So the work of this force in here, or minus mg, I can write it as minus du dy in this case, because I'm using the y coordinates for the height. So if I integrate this expression again, this one will go to 0, that the potential, gravitational potential energy, I think he used the symbol S for this one and G for that one, it's mgy, plus some constant, okay? The constant tells me where to choose the origin of the potential energy, that's all, okay? So in this case, the potential energy for the gravitational potential depends on how high you are from some points. So it matters mg times h. You guys remember this expression too from your physics 4A?
Yeah.
Okay, very good. So this is the stuff that we're talking about in here when it comes to the electric field. So the electric field so far has the force for the electrostatic force. That's what we're calling over here, the electrostatic force. Electrostatic force is basically F equals to QE. That's basically the whole purpose of chapter 21 and 22 was to find this force, actually. Yes, we went through the Gauss's law to find E and so on and so forth, but that's not an end in itself. That's really the force that we're trying to find. And this force is in Newton, by the way. Okay. Here is a question. Does this force derive from a potential? That's the question we want to know. Okay. If it is, then the work of this force is conservative. If true, then this force is conservative. That means it doesn't depend on the path. Of course, if it's not, it's like friction, conservative. That means it's like friction and the engine and all of that thing. We want to know that. Now, instead of answering this question that way, we can answer the question differently. Because Q is a number. Q just is a number, like 12 and 23 newtons or something like that. I know one of you guys sent me a message yesterday finding the charge in one of the problems being 8,700 newtons or 7,800 newtons, 8,700 coulombs. That is too much of a charge, by the way. Most of the time of these problems that we have, the charge should be of the order of a microcoulomb or a nanocoulomb or even a picocoulomb. So when you see yourself finding charge of several thousand coulombs, that's when you have to be very, 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 very suspicious that you may have done something wrong, okay? But it's a number nonetheless. Even if it's 0.000007 coulombs, it's still a number, okay? So instead of answering this question, whether or not this force, the electrostatic force, is a conservative force or not, I'm going to answer the question, the following question. Is the electric field itself derived from a potential? If we answer that confirmatively, if we confirm that indeed the electric field derives from potential, then indeed the force must be deriving from potential. You guys see that? Because that's just, you're multiplying it by a number, by scalar in this case, okay? So what we're saying in this case again is that does F for the electric field equals to something, something U. I'm going to plug in what that something need to look like, okay? It's going to be a gradient, actually. Have you guys had the gradient somewhere in your classes or not?
Yes, I've seen it before.
Okay, so I'm going to write it down, but we're going to go through the exercise of understanding. If you have never seen it, please don't jump from your scale, from your thing. It looks like this. A delta backward, okay? So this is the gradient. In some other textbooks, you write it actually as a grad of u. As a whole word, okay? It's the same thing. It's just a notation. This is sometimes called nabla. Nabla, okay? I don't know which language that is. Maybe some Greek letter or something. But it's a delta backward, okay? So if you have never seen it, that's what it is. Why do I have to use that symbol? Because I'm not dealing with 1D. Actually, we should have used that symbol too when we were doing physics 4A, but we were doing only with 1D. So 1D, we were doing just a simple problems. We didn't have to worry about them. In other words, here is what that operator is. So here is what we're saying in here. When we have more than 1D. In 1D, the force only has one component, and we say it's minus du over dx. In 2D or higher, the force has more than one component. It has an fx or an fy component and or an fz component. So the force potentially is a vector. I mean, it's not potential, it is a vector. So the force in 3D, for example, has an x component, has a y component, and has a z component. And I need to write them in terms of this u, where a big U is what I'm calling, in this case, the potential. Okay, potential energy. U is measured in the same units as the kinetic energy, as much as the work and everything else. So U has the units of joule in joules, okay? So I cannot write it. First of all, I have to have the minus, and the minus is actually for cosmetic reasons, as I was saying. Otherwise, we'll be dealing with adding the, subtracting the antiderivative of the work, and people didn't like that. And for aesthetics only, they plugged in the minus in the definition of the antiderivative, and then basically had, instead of saying that the mechanical energy is the difference between the kinetic energy and the antiderivative of the work, they said no, it's actually the kinetic energy plus potential energy. Potential energy defined as being the antiderivative, the negative of the antiderivative of the force in this case. Okay. So here is the thing. So I have to take a derivative of this u with respect to x. I have to take the derivative just to draw parallels with this thing. Okay. And I already did it for the spring with respect to x and for the weight in terms of y, because gravity in this case points in the y direction, and spring we took it horizontally. That means it's in the x direction. So this derivatives of u better be in the y direction. Now, in general, in the z direction, it has to be with respect to x. So I have some derivative in here of a function u that does not depend on a single variable. It will depend on a single variable if we're actually doing one-dimensional problem, like for example, a spring on the horizontal direction, how much compression or elongation of the spring, or the weight, how high we are. But this thing could depend on both x and y, and actually z too. There is no reason for it not to depend on all of the three variables. Okay. Here is the biggest lie that you have been told so far, that a function like this exists anywhere. This is not true. Single variable functions are actually an exception. In order to find something that depends on a single variable, you really have to do a lot of work in the lab to do that. You have to basically fix all of the other unknowns and just keep one independent variable and see how the dependent variable vary on it. So it requires a lot of caution in the lab, a lot of work on your part to basically control all of the other parameters in order to find that. But in real life, everything depends on more than one variable, like the temperature, for example, this temperature right now. It depends on time. It depends on the day, in the morning, in the afternoon, on 3 days from now, on a month from now, in the summer, in the winter. So it depends on time. We know that for a fact. It depends also on the location. And here in Southern California is different than Illinois, is different than probably the North Pole or maybe the Himalayas or somewhere else. So it depends on location. So those are two variables already. It depends on the pressure, okay, for sure. Okay, it depends on the insulation in the room. It depends on it depends actually on the device that is measuring it, if it's faulty or not. Okay, so that's the reading. It's not an actual function, but again, that is so many parameters are actually involved just in that parameter, that the temperature, that you cannot really plug in temperature as function of time and tell me that this is how temperature changes from day to time. So it increases then in the noon and then decreases in the evening and then so on and so forth. So that is an idealization, if you wish, in the same location. So you make sure you do the experiment in the same place. You don't move it. So you have controlled, in this case, the location. You maintain the humidity the same in that location and the pressure the same in that location. And you make sure that the windows do not open and close, because you will see kinks in this thing in here that you cannot explain them because during those things. And you have to have so many things to make sure that this is behavior like this. So this is not real. This is a mathematical idealization that requires a lot of work from you in the laboratory to make it happen. This is more real. This is real stuff. So the business where we were dealing with a D with respect to anything, like this function with respect to X, this is just an idealization. This symbol is really not real. This is an odd thing to see. So if you see the straight D in the derivative, understand that you're dealing with an exception to the rule in an ideal situation that does not exist in real life. Everything depends on so many parameters that you really have to work very hard for you to find that situation. What you really should be finding is another way of writing this derivative. You're fixing everything except that one. So what you're saying now, I want to find the derivative with respect to X. Granted that this function depends on so many parameters, then fix everything else and take the derivative with respect to that variable. This is normal. This is odd. So just to make the distinction between the two, we write this curly D in here. That the D, instead of going like this, it goes with a tilt in it. Okay, so we write it like this. Okay, just to indicate that we're doing a derivative with respect to a variable and keeping everything else constant, because we're dealing with the real stuff. Okay, so this is called the partial. I know I sound like I'm doing an infomercial, but I'm hoping that you guys buy the argument that it's more of a natural thing to see this than what you guys have been used to so far in calculus if you have never seen this stuff. What you've been told so far was just an idealization to just show you how to get started on things. In real life, you're going to be dealing with this curly D, which is called the partial derivative. Why is it partial? Because this function can depend on so many variables, and we're doing a derivative with respect to this part of it only, not the entire thing. Does this make sense to you guys?
Yeah.
Okay,
It was,
so let's
yes.
practice. Sorry, let's practice a little bit with this business in here, because it might look daunting, but it is not that scary really when you do it yourself, okay? It might look kind of scary, but there is no harm in it too at all. So let me take a function u, for example, up to just two variables, and those variables are x exponential xy. So this is clearly a function that depends both on x and y, okay? And I want to find, so this is the item of the discussion today. I want you to complete this task, okay? Complete it. Of course, every time I do a calculation in the class, namely problems, you're supposed to finish them on your own if I don't do the plug in the numbers. Although problem 53, I did it in detail, but if you find an argument in it that is not correct, that is part of the discussion too. Please bring it to my attention and everybody else that there was something flawed that we solved in the classroom, because I told you guys I make mistakes. So please go through them, make sure that If there is something that is not correct, correct it and let me know and let everybody know so that everybody benefits from that, okay? So that's still true for any kind of problems. And then there is a plug-in numbers problems where I ask you guys to do your own calculations and also plug in the numbers, because most of the time I do just rough estimates for the numbers. Basically, I do just an order of magnitude, and you're supposed to come up with the correct answer in there and see whether or not the order of magnitude matches the correct answer or not. And whether or not I may have overestimated or underestimated something, and maybe it's a completely nonsense, okay? So you're required to do those calculations with the calculator and so on and so forth. But for this one, this is an example. And you can pick up your example of your liking if you like, okay? I'm going to take du with respect to x. If I do that, that means y is constant. That's what this curly thing is saying. So y, this y is just a number like 12 or 17 or 23. It doesn't matter which number you like, okay? So I'm going to take the derivative with respect to x, and I have to use, in this case, the product rule. The derivative of the first is 1 times the second plus the derivative of the second times the first. So this is the first times the derivative of this guy. What is the derivative of exponential x, y with respect to x? Stuff from calculus, this one has nothing to do with physics. What should I do? I'm taking the derivative. Think of this one as any number, a, for example, exponential of ax. What is the derivative of exponential ax? This is calc stuff, guys. We drop this number and we keep the exponential, don't we? So this is y exponential xy. Does this make sense?
Yeah, now it's coming back.
Yeah, okay. So it's basically because the derivative of the exponential is exponential, but you have to take, this is actually the chain rule, honestly, because you're taking the derivative of the argument with respect to x. So you drop, because y is constant, and then you're multiplying by the derivative of the exponential with respect to its argument, which is in this case the exponential. So again, this is just exponential xy times 1 plus x times y. So that is the derivative with respect to x. Now, we're going to do the same derivative with respect to y. Clearly, this function, again, we're going to use the same rule, but in this case, x is constant, so it's just going to stay there. So it's going to be the derivative with respect to y, not with respect to x. So again, x is constant, so it's going to drop in here, and it's going to be exponential of xy. So this derivative is x squared exponential xy. Okay, simple as that. Okay, so obviously this derivative is not the same as the other derivative. You can clearly see this has 1 plus xy. This one has x squared times both of them the same exponential. So that is a good thing to remember. Now here is what I want you to do. I want you to, I know we still have 2 minutes before this one is over, and I've been borrowing from your time for a long time now. So we're meeting at 5 anyway. So we're going to take the derivative with respect to y of the derivative with respect to x. If you don't know how to do it, please let me know, because this is interesting for later on when we do the curl, actually, when we get into magnetism and stuff like that. Okay. Here is the derivative with respect to x. Plug it in here and find this derivative. So this is the mixed derivative. You can't do this in a function of one variable. There is no such a thing of mixed derivative because there is only one variable. You only have the second derivative in that case. This is actually a mixed derivative, okay, of the second order in this case, because you have to switch these two things. So plug in this function that we found in here, plug it in there, and do the chain rule. I mean, not the chain rule, I'm sorry, the product rule, okay? Don't forget that in this case, you're taking the derivative with respect to y, not with respect to x. So the derivative with respect to y of this whole thing would be just x. And the derivative of respect to this one with respect to y would drop another x. So you'll have an x squared something in here times plus another one in here. So there is a chain rule there at work, okay? I'm sorry, the product rule, I'm sorry. The derivative of the first times the second plus the derivative of the second plus the times the first, okay? So we're done with that part. We're going to do also the derivative with respect to x of the derivative with respect to y, derivative of u with respect to y. So in other words, take this last result that we found in here. This is du with respect to y, and plug it in here. And you're going to find an answer. So this is the next derivative in the other order, though. The first one, take the derivative with respect to x first, and then take the derivative with respect to y. And the second one is take the derivative with respect to y first, and then takes the derivative with respect to x. And you will find an interesting result. And the interesting result is that I want you to verify that these two must be equal. Doesn't matter which order you do them, the two derivatives will be equal. So, but I want you to go through that exercise, okay? If you have difficulty with this one, or if you need help with it or something, this is something that probably we can, we should be able to practice on, because we will probably do stuff, but not to this extent, honestly, okay? So we're gonna be dealing with multivariables, but not to this extent. I want you to be at ease with this concept, that's all. So all I want you to do is write this curly D as much as you can, because we're gonna be needing this symbol at least. And from chapter 23, I know we're out of time right now. From chapter 23, we'll have a bunch of problems. One of these problems is problem 76. Problem 76, actually, I tested on it in the past. And if you look at problem 76, it's actually the potential is given as a function of x, y, and z. So you need to do this stuff for it to find the electric field that derives from, that gives me, that is, derives from that potential, yes, in problem 76. We're going to also do problem 77 from that book. We're also going to do problem 61. We're also going to do problem 41. We're probably going to, if we have time, to do problem 46. And the problem 57 is a very powerful problem that we probably have to explore though too, because it talks about the ionic structure of for NaCl, for salt, okay? Problem 62, which is a very good problem also, we may do that too. So we have a lot of problems. That's the Geiger counter. And problem, what was the problem that I looked at and I thought is a wonderful problem? Problem 72, actually I tested it in the past. So that is actually an interesting problem. Another problem of a beautiful problem is problem 80. That's applications with biology. I'm not going to do that problem, but I left that for you two guys to explore. So there's so many great problems in this chapter, but you need to have an ease with this symbol. That's the purpose of this discussion today. Okay. I know I'm 3 minutes over your time limit. I will see you guys at 5 o'clock this afternoon, where we finish this discussion and do some great problems from chapter 22 still. Good?
Good.
Sounds
Thank you,
good.
Professor.
Thank you guys. See you this afternoon.
Mhm.
Take care.
Take care.
You too. Okay, thanks.